Good afternoon, grade 12s, and welcome to another Cation science tutorial. In this lesson, we will be tackling the Ka table and looking specifically at how to solve a problem using this Ka table. Now, this is really important work for the upcoming exams, especially with a focus on prelims and your final exams, as this table is very often asked, and this table can count up until 12 marks in a grade 12 South African exam. So, really important stuff. That being said, I'm going to approach this problem with my highlighter in hand, and I recommend that you guys do the same in your upcoming exams. It's always just helpful to sit with a highlighter or a colored pen so that you're not rereading the problem and rereading, but that you're focusing on the important information, taking it out, and approaching the problem in such a way. In this specific problem, they're telling us that 0.1 moles of HF is dissolved in 1 cubic decimeters of water. And then they're asking for us to determine the Ka of HF if the pH is found to be 2.1. Then they're kind enough to tell us that HF dissociates according to the following chemical equation. Grade 12 is important to note that they don't always provide these equations in your grade 12 exams. So it's important that you understand how to come up with a balanced equation on your own if they're not providing it. That being said, I took the opportunity to write out the blank Kc table for you guys, in this case the Ka table. And I took the keywords, and I just want to take this opportunity to just show everyone how to memorize this table, because again, in your upcoming exams, it's not necessarily the case that you will receive this blank table, but it's something that you need to memorize. Typically, the question may be exactly like the one above, and they're just asking you to solve this problem, not providing the table. And then, as I've already mentioned, a lot of the times these questions can count up until 12 marks. So it's really important that you memorize this table. That being said, if you guys look at the table and look at the headings, we can see that the acronyms included is basically RICE with two E's. And if you memorize RICE, you will kind of be able to write down this blank table with ratio, initial mole, change, equilibrium, and then equilibrium concentration, remembering rice with two E's. And I'm just going to write it here on the side so that everyone remembers this. So it's rice with two E's. That being said, at the top, we're going to include everything that we need for this Ka table. Now, grade 12s, furthermore, it's so important to remember that everything is not included in a Ka, Kc, or equilibrium constant value, but that only the AQ values and only the gas values should be included in your Ka table. So in this case, I'm completely going to ignore water and I'm only going to be interested in the AQ. That being said, you should be able to write the base equation for your Ka value, and that is products to the power of the mole in front of them over the reactants concentration to the power of the mole in front of them. So just starting off with where we're heading, as they are asking the Ka value, and the Ka value is going to be equal to the hydronium concentration, H3O plus, to the power of the mole. In this case, we only have a 1 in front of it, so we don't have to write it. You can if you want to, but not necessary at all. And then it's going to be times the F minus also the concentration. That's why we have the square brackets. And we're going to put that over the reactants. And important, we're ignoring the water because it is a liquid, and we are only including AQ and gases within this Ka value. So we're going to say that over the HF concentration. And grade 12 is important to know that as we're working out an equilibrium constant, that these concentrations need to be at equilibrium. And that's why we need the table to solve this problem, and that we can't just take the 0.1 mole HF and divide it by the 1 mole over the volume and substitute here for concentration values, because that's not necessarily the concentration at equilibrium. So we want to get here to the bottom of the table, where we will figure out the equilibrium concentrations. Now, this table, depending on the exam and depending on what they're providing you with, you're going to populate it from a point, and you're literally going to fill in as you go along and as you figure things out. So that's why I say kind of memorize the blank table, and you can populate it from there. So that being said, on the left-hand side, let's just go ahead and write this equation. So on the reactant side, we have the HF, and this is reacting to form the hydronium H3O plus and the F minus. Notice again where I'm getting this from, directly from the equation. And also I'm ignoring the water because I'm not interested in liquids for the Ka value. Then I'm going to populate the ratio, and the ratio is coming directly from the mole ratio. So I'm literally checking the numbers in front of this. In this case, it's 1 mole of HF, 1 mole of the H3O plus, 1 mole of the F minus. So it's going to be in a mole ratio of 1 to 1 to 1. Now, this mole ratio is so crucial, guys, because the change in mole is always going to take place in this mole ratio. So I'm just going to go ahead and make the change in mole column orange. And I'm going to demonstrate in just a second how we're going to use this mole ratio to figure out the change in mole. And it's always going to work like this. The change in mole is always going to be taking place according to the mole ratio that we just populated above. And then we're going to have a look at the initial mole. Now, great tools, remember, you're starting with something. For example, in this case, you're starting with reactants and it is producing products. Initially, we don't have products because the reactants haven't reacted yet. So it's important to understand that initially we're starting, unless they're stating otherwise in the problem very specifically, unless they're stating that we're making the assumption that initially we don't have products because they haven't formed yet. So that's why I'm going to make both of these products 0 and 0 because initially we don't have products. To start with the reactants, they told us we're starting with 0.1 mole HF, and I'm thus taking it directly here above, and I'm just going to write we're starting with 0.1 mole HF. And then if we read further, they're giving us the pH value. Now, you know from what you have done in class and what you've memorized, and by looking at your formula sheet, that you can use the hydronium and the pH. You can use the pH that they're providing to figure out the hydronium concentration at equilibrium. And if you figure out what the hydronium concentration is at equilibrium, we can kind of backtrack that into figuring out one of the changes, and then we're going to use this mole ratio to figure out the rest of the changes. So let me just quickly demonstrate. Directly from your formula sheet, you know that the pH is equal to negative log of the hydronium concentration, H3O plus. Again, why are we doing this? Because we're trying to figure out the hydronium at equilibrium so that you can figure out the change in moles so that we can populate the rest of the columns. Now, if we just go ahead and do the inverse of the log, we're going to get the hydronium concentration, H3O plus. And by the way, great ones, don't overthink this. You can do this on your calculator, so don't overcomplicate the inverse. It's going to be to the power of negative 21. And then if you pop that into your calculator, the hydronium concentration, H3O plus, is going to be 7,94 times 10 to the power of negative 3. Remember, whenever you're writing anything in a science paper, it needs to have a unit, and the SI unit always needs to be indicated. So in this case, it's going to be mole per cubic decimeters to the negative 3. And you have just managed to figure out the equilibrium concentration of the hydronium. So I'm going to write that into the right block, 7,94 times 10 to the negative 3. Now, in the specific problem, they've made your life very simple in the sense that they gave us a volume of 1 cubic decimeters. So actually, if you just go ahead and work out the mole, or the concentration in this case, is going to be equal to the mole over the volume. In this case, as I've mentioned, the volume is 1. So if you're trying to then backtrack from this equilibrium concentration and figure out what the mole is going to be, it's going to be exactly the same, because we're basically dividing by what the equilibrium mole divided by 1, which is the 1 cubic decimeters of water, or the volume, to get the concentration. So we're making the assumption from that argument that the equilibrium mole is also going to be 7,94 times 10 to the negative 3. Now, this makes our life quite simple because now we've managed to figure out most of the columns, and we can kind of wrap up the hydronium one, and then we're going to utilize the mole ratios to figure out the rest of the columns. Let me demonstrate. Now, another thing before we jump into this, guys, when you're trying to look at the change in mole, it's important again to have this argument that we are basically using up reactants. So everything reactant wise is going to decrease, or the change is going to be a negative value with deducting there. And with in terms of your products, everything is going to increase because we're producing products. So this is going to be a plus, and this is going to be a plus. So that's coming from your argument as I explained now. Then we're going to look at the initial mole for the hydronium, which was 0. And I'm going to say 0 plus what gives me 7,94 times 10 to the negative 3. And in this case, it's very simple. It's going to be plus 7,94 times 10 to the negative 3. Now, grade 12s, as I mentioned, this entire orange column is coming from your mole ratios that are indicated above. So you're going to use that mole ratio to figure out the change in mole. I'm just going to demonstrate this very quickly on the side. If they weren't kind enough to give you a lot of 111 mole ratios, so just so you can see the math happening here. So typically, and this is coming from grade 11 work, you would have taken the two reactants and products in this case that you are looking at the mole ratio. This is going to be H3O plus, and they are on the mole ratio of 1 to 1 with regards to each other. Then we have the hydronium, which is 7,94 times 10 to the negative 3. And most of the times, as I mentioned, they're going to make this one x. And to figure out that x, I'm going to say, I'm going to cross multiply. Let me just do this in green so you guys can see. 1 times x, 1 times 7,94 times 10 to the negative 3. And you then are going to conclude that x in this case, as it is a 1-to-1 ratio, is going to be 7,94 times 10 to the negative 3. And as we are sitting with a lot of 1-to-1-to-1 mole ratios, I'm going to make the assumption that they're all going to be the same. So I'm taking that number and populating here. Again, the negative is coming from a previous argument. So I'm going to say 7,94 times 10 to the negative 3. And I'm going to say plus 7,94 times 10 to the negative 3. And then I'm going to progress from there to calculate the equilibrium mole. So I'm going to say 0,1 minus the 7,94 times 10 to the negative 3. And if you pop that into your calculator, it's going to be 0,092 mole. I'm going to do the same for the other side. 0 plus the 7,94 times 10 to the negative 3. And that's going to be the same as the hydronium. So it's going to be 7,94 times 10 to the negative 3. And then to calculate the equilibrium concentration for those two variables, as I've already mentioned, they're being very kind because they're giving you 1 cubic decimeters of water. So in this case, to figure out the concentration, it's going to be the mole 0,092 divided by 1, because that is 1 cubic decimeters. The SI unit is already correct. And you're going to conclude that the concentration is going to be 0,092. You're going to do the exact same thing on the other hand, and then you can conclude that this concentration is going to be 7,94 times 10 to the negative 3. Now, this is wonderful, guys, because this is actually what we have been attempting to solve in this very elaborate problem. And this is the whole goal of the table, to figure out the equilibrium concentrations so that we can pop it into the Ka table. So then progressing to do so, we're going to go ahead and just substitute the column here at the bottom. And we're going to take the hydronium concentration as the 7,94 times 10 to the negative 3. And we're going to multiply that by the F minus, which is also 7,94, 7,94 times 10 to the negative 3. And that over the HF, which in this case was 0,092. And you're popping everything in your calculator. Please don't try and do it without a calculator. You should always be showing up with your calculator in hand. And then popping everything in, and you're going to get a final answer of 6,85 times 10 to the negative 4, which is your final answer. And in this case, we're looking at an equilibrium constant, so it doesn't have a unit. And I want to close off this lesson by just showcasing how typically in a grade 12 exam, how this type of question is typically marked. What are they looking for? A lot of the times, in a grade 12 paper, not a lot of times, what is always important is your formula, right? So whenever you're doing anything, guys, please show your formulas. You can see, for example, the pH formula, you're going to get marks for that. You can even get marks for your substitution here at step number 2, and then figuring out the hydronium concentration. Depending on your teacher and depending on the paper and how they're marking that year, you may get the mark here, or they may just check all the rows and checking that everything in the row is correct. So a lot of the times this is marked, everything in the row is correct. Everything in the row is correct. Again, again, again. And grade 12, you can see this really adds up to quite a bit of marks. And as I've already emphasized, make sure that you have your equation for the Ka value. So getting a mark for that, getting a mark, a lot of times they mark top correct, bottom correct, final answer. And that is then a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 marks. Depending, again, as I said, on how they mark, they may even allocate another one, equaling this question to a 12-mark question. I want to invite anyone, if there's any questions, you guys are welcome to comment on this. I will be providing you with further videos and further support in the weeks to come. And I want to wish you the best of luck for your exam preparation.